Hey guys, Chili here. Welcome back to Project Twin. Today we are going to be working at a lot of the deep stuff about the engine. We're going to implement a Codex system, a resource management system that is going to manage all of our surfaces, and eventually it's going to be managing all of our loaded resources. And we're also going to be implementing a binary search algorithm for our codex of surfaces. Alright, now the next system that we add here is going to be a big one. We're going to be improving this as we go. But here is the first draft. As I call it the surface codex, and it's going to be a central repository for all the surfaces that all the entities in our game use. But before we look at the codex itself, let's take a look at why this is actually super necessary. So if we look into poo.h, we see that every poo embeds a surface poo. That is the sprite that is going to be drawn. So if we've got 100 poos, we've got to load that same surface 100 times. It's not that big of a deal because the sprite is small and there's only one frame. But now imagine an enemy where you've got maybe hundreds of frames of animation altogether, and you've got hundreds of instances of that character being loaded. That's tens of thousands of frames of animation all clogging up your memory. And you might think, well, computers, they got like gigabytes of memory now. We don't have to worry about this bullshit. And that is true, but it's also false, because although you have gigabytes of your normal RAM, you also only have a few megabytes of your very fast cache memory. So you still have to think about the size of your data, especially for things that you're going to be using very often, like images for sprites here that we're drawing. You got to think about maybe keeping that as small as possible to maximize your utilization of the fast cache memory in your CPU. So we don't want to be duplicating this stuff if we don't have to. We want to put it in a central place, and then all of the entities can have references to it. And that central place, I call it the codex. So the surface codex is gonna have a vector of entries. What is an entry? Well, that's just an inner class of the codex. An entry has a pointer to a surface, and it has a key, which is basically the name of that surface. And what it does is, well, this is what we call a singleton class. So there can only be one instance of the surface codex. And how do we enforce that? Well, the constructor for, if you notice, for surface codex, the constructor is private, so you can't call the constructor yourself. And how you construct an instance of this is there is a static function called get. And what get does is it creates a static instance. So the first time you call this, it will create a static, which is basically a global that can only be seen from inside this function. But it creates this instance of codex, and then it returns a reference to that instance. So whenever we want to do something with the codex, we call get. The first time we call it, the codex will be created. After that, the same created instance will just be returned. And then we've got a few functions that we can use here on the codex. The destructor just deletes all of the surfaces in all the entries. And then we've got the functions retrieve and purge. And what retrieve does is it uses findIf to find a matching entry. So if we're looking for, poo.bmp, it will search for poo.bmp in all the entries. If it finds it, then great. We just return that. We return the pointer to the surface. If it doesn't find it, then what it has to do is it has to load the surface and add that to the vector of entries. So what the client does is it calls retrieve, it says get me surface of this name, and the client doesn't need to know whether it's been loaded or not. It just says give me this, and the codex will determine whether or not it has already been loaded. If it has already been loaded, return a pointer to the already loaded surface. If not, load that surface, store it in your database, and then return a pointer to the stored surface. And then purge here just deletes all of the things, which can be useful if you're doing like transition between two levels. You want to delete all the surfaces from the old level because many of them may not be used in the next level. And these are all private here. And then for the public interface, surface codex, I just add a couple of static functions, retrieve and purge. And retrieve just calls get, and then uses that to call the retrieve member function. So this is great, this is fantastic, amazing, but it's going to require a few changes in our entities now, because now we're not dealing in references and in actual objects, we're dealing in pointers. So for poo.h, if you go down here you're going to see surface poo has been replaced by constant surface pointer to poo surface. There, that sounds great. So now we've got pointers to things, and then what we do is when we're drawing, we've got to dereference those pointers. And now when we're loading, we call surface codex retrieve and then images /poo.bmp. And there you go. And that's how you do it. And in chili.h, it is much the same story. Instead of surface head and legs, you've got the pointer to the head surface. Because the chili, it draws the head itself, but it doesn't draw the legs. The legs are just passed as a pointer to animation, so we don't have to maintain our own pointer to the legs. So what we do here is we call retrieve here to load the pointer for the head, and then for the animations we get just a local pointer here to the legs. We retrieve that, we pass that pointer to both of the animations for walking, and we don't have to store that pointer ourselves in Chili. Only the animations need to know about that. And then again, when we draw, we have to dereference the pointers. That's all that this stuff is doing here, dereferencing the pointer. Now, the story is much the same with bullet. It no longer needs to hold the surface. It just loads the pointer directly into the bullet animation. But there is one big difference, because remember before we had the problem of the bullet animation referencing the bullet surface, and then when the bullets got copied, the shallow copy of the bullet animation would fuck us over. So we had this whole copy constructor thing here, but we don't need that anymore, because we're no longer referencing an embedded surface now. We're referencing the surface that is loaded on the heap and managed by the surface codex. So now it's stable. It's no longer subject to the whims of the vector container. So we don't need this fucking copy constructor bullshit. I don't think we even need this one, but I forgot to remove it. I'll remove it later. But yeah, this is a huge update. It doesn't change anything about the game visually. I'm not going to show you a demo because it's the same as what we had before. But under the hood, this is much, much better. It's going to make our life a lot simpler, and it's going to get better in the future. So the next thing I do here is I adjust the boundaries for the bullets a little higher so that it looks like they hit the wall at the appropriate height. So what I do here is I've added a little utility function to rectangle get displaced by and get displaced by. Just displaces the rectangle by a vector, which can be very useful, and then I do that in here. So I'm displacing the boundary rectangle up just by 10 pixels here. It's just a little bit of a magic number in here. Later on, I'm going to give projectiles and other things a proper height that they are drawn at, and that is going to affect their physics. But for right now, just going to displace that boundary rectangle up by 10 pixels. And a few other, cosmetic changes. Change the walk animation speed, make it a little faster. Here, apparently we were leaking memory like a motherfucking sieve. So Surface Codex apparently had a problem. And the problem was, so we're creating a new surface here, and then we were inserting another new surface. So this is not a really good situation. We're inserting one surface into the codex, we're returning the first surface that we created. Terrible, terrible idea. So we should create the surface, insert that into the codex, and then return that same created surface. Further improvements on the surface codex is we make the surface a const pointer, and we return const pointers so that nobody can modify. Because imagine you've got 100 sprites sharing the same surface. If one of them makes a change to that surface, that's going to appear on every character. We don't want to allow that. So here, constness will protect us, will tell us when we compile that we're doing something really stupid, maybe we should reconsider our life decisions. So constness is really nice here. And another little improvement to the surface codex, when you get a lot of surfaces in there, what we were doing before is we're basically doing a linear search. So this find if would scan through every entry until it found one that matches. Or if it doesn't find one, it scans through every entry and then returns, iterator to the end. But we can do that better. If we sort them, then we can do a binary search. So I call this binary find function. That's a function that I've created. And binary find will find the entry generally in log n number of comparisons. So So let's say we have container, we want to search for an element. Linear search is just going to go through each one, basically a for each loop, and it's going to run until it finds it. Binary search, what it does is if your container is sorted, what you can do is instead of starting at the beginning, you start at the middle and you check this one and you see, is this one the one I'm looking for? No. Well, is it greater than or less to? So if it is less than the one I'm looking for, because this is sorted, I know that the one I'm looking for must be in here. So then my next search is going to be in here. I can eliminate half the container in one comparison. Next time I search, I'm going to search in the middle of this region here. I'm going to check this one. Is it the one I'm looking for? No, it's actually greater. So now I know my my area of interest is now here. Next I search here. So every time you are cutting the amount of elements that you have to search in by half. So the actual math for this if this takes on the order, we could say on the order of n comparisons, this one takes on the order of log n, typically log 2n. So what does that actually mean? Well, if you got a container with 1,000,000 entries, it's going to be on the order of 1,000,000, right, for the linear. But if you go log 2 of 1,000,000, the answer is about 20. So what would you rather do? 20 comparisons or 1,000,000 comparisons? That's the difference between a binary search and a linear search. Now, obviously, in our situation here, we're not loading that many things into our codex, at least not right now. So it's not that big of a deal. But it's, it doesn't hurt. And I just wanted to do it, so I did it. I didn't do it because I had to. I did it because I wanted to. So yeah, here we do a binary find, and then if we find it, if we didn't find it, then we load and we put it in the correct place, because now the main downside to doing binary search is you must maintain a sorted container. It has to be sorted. So here we have to insert it into the correct place into the container. We can't just push back. So we insert the entry whenever we don't find it, and then we return that. Actually, later on, this will be simplified even more. But for right now, that's how it works. And the find if, it's just a function I've added to Chili util here, binary find. And it takes a functor that allows you to access the thing that you are looking for. So this enables it to work with any kind of functors right here. This enables it to work with any kind of custom type. So we use the standard library function lower bound, and lower bound will find the lowest element that is either greater than or equal to the value that we're searching for. And then once we find that, we just got to figure out whether it is the one we're actually searching for or whether it is the one that's greater than. And if it is the one that's greater than, then this is actually going to be the place where we want to insert our value. And that's why here, if we see that it doesn't exist, we have to do another lower bound to find the position to insert. So later on, I'm actually not going to call binary find. I'm just going to call lower bound from the beginning, because then we don't have to call it twice. But you'll see that later on. And the last thing I did here was I realized that we don't need the copy assign either, so I've also deleted this one as well. That's going to do it for today. I hope you like this under the hood nuts and bolts data structure stuff, because we're going to be having it for the next few videos, so stay tuned for that. But until then, thanks for watching. Hope you enjoyed the video. If you did, please click the like button, it helps a lot. And I will see you soon with some more Project Twin.